In this video, we will cover the characterizations of invertible matrices. Much as this video is devoted to the invertible matrix theorem. It's a very powerful theorem. So here is our overview slide, which I'll spend about 5 minutes to give you a sense of what we will be covering. And then afterwards, we'll go back over each topic with more detail and plenty of more examples. So to start with our overview, as I mentioned, we will be going over the invertible matrix theorem. And the two things to know is this is a very powerful theorem because it connects so many important concepts. But the other important thing to note is that this theorem applies only to square matrices. We will also be looking at what happens when we multiply two square matrices. So if AB equals I, then we say AB are both invertible with B equals A inverse and A equals B inverse. And a reminder, singular matrices are non-invertible. Non-singular matrices are invertible. And last, we'll be talking about invertible linear transformations. Remember, linear transformations can be represented by matrices, but we'll be talking about transformations and inverse transformations in particular. So we'll define what it is to have a invertible transformation. So we say a linear transformation T from Rn to Rn. Remember, this video is devoted to square matrices, is said to be invertible if there exists a function s from Rn to Rn such that s composed of t of x equals x and t of s of x is also equal to x. So it's kind of what you would intuitively think of as invertible. And then we have this theorem that says that t from Rn to Rn, if it's a linear transformation and A is the standard matrix for T, then T is invertible if and only if A is invertible. So that's it for our quick overview. So the next thing we'll be doing is looking at the invertible matrix theory in more detail. We are going to start by talking about these without proofs, but it's a good review of different concepts because it, as I said, it connects so many important concepts. So this will be a good review of important concepts. And I will also say it's a review, but it also, if something doesn't follow kind of quickly, it might be a good clue to go back and maybe do some review of that section. So first I'll just talk about some of these points that we can kind of quickly get some intuition for. The invertible matrix theorem says, let A be an n by n matrix. And again, pay attention that this is a square matrix. Then the following statements are equivalent. And by equivalent, that means either they are all true or they are all false. So if one is true, that makes all of them true. If you find one statement is false, that makes all of them false. So the first statement is A is an invertible matrix. The second statement is A is row equivalent to the identity matrix. What I'm going to say next is not a proof of anything, but it is something to give you a sense, some intuition. So we know that these two are equivalent because in order to find the matrix inverse, what we did is we row reduced A right along with next to I until A was reduced to the identity matrix. So we can look at this from a previous video. We have this theorem that an n by n matrix is invertible if and only if is row equivalent to I. So this is exactly the theorem that proves these two. And what we used is any sequence of elementary row operations that reduces A to I also transforms I to A inverse. And so if we had A, we wrote the matrix A alongside the identity matrix, and we row reduced. We did all these row reductions until eventually our A matrix became the identity matrix. And while we were doing the row reducing A and doing the same operations on the identity matrix becomes A inverse. And these are equivalent to C. A has n pivot positions. We'll look at this later when we do the formal proof. D, the equation AX equals 0, has only the trivial solution. And I'm just going to point D back over here. So if A is row equivalent to the identity matrix, then we can row reduce A to I. And then AX equals 0, this equation here, becomes the identity matrix times x equals 0, which has only the trivial solution. Now this next statement, the columns of A form a linearly independent set. You can see how that's equivalent to D because D, AX equals 0, has only the trivial solution, is literally the definition of the column vectors of A form a linearly independent set. This next statement, the linear transform from x to ax is 1 to 1, that's a little bit more complicated. But we did prove that D implies F when we were talking about linear transformations, the matrices of linear transformations, and we did this by contradiction. This next statement, the equation ax equals b has at least one solution for every b in Rn. Well, if A is invertible, then for every b in Rn, we can write that when we have the equation ax equals b, we can multiply both sides of the equation by A inverse. That would become the identity matrix on the left-hand side, and we're left with x equals, then we have A inverse b. So therefore, x is the solution for any given, x equals A inverse b is the solution for any given b. For G, for G implies H, the columns of A span Rn. So what we have is for every b in Rn, from G we can find real coefficients x, the vector x, which also is x1, x2 up to xn. So the real coefficients are x1, x2 up to xn, such that a1 x1 plus a2 x2 plus an xn is equal to b. This, where a1, a2, and an, those are the columns of matrix A. And we've already said from part G that this A times our vector x equals b has at least one solution. So therefore, we can find these real coefficients, and then b becomes a linear combination of our column vectors of A, which is exactly the definition of span. So for this next one, that the linear transformation maps onto Rn, well, the definition of mapping onto Rn means you can find an x that will map to every vector b in Rn. So for all b in Rn, there exists an x which is equal to A inverse b, and we know there's an A inverse because A is invertible, such that Ax equals b. So that's the definition of onto. So I think we've done enough little examples, so I'm going to stop here and I'm going to do the formal proof. So the proof is quite long, but one thing we are not going to do is prove that each statement implies the other. We're going to do this in a circle. We're going to apply that, prove that A implies J, which implies D, which implies C, which implies B, which implies A. So there's the circle, so if you wanted to prove that D implies B, then you just go through these steps. You would prove D implies C, which implies B. Or similarly, if you wanted to prove that B implies J, you would go through the steps of showing B implies A, which implies J. So this is one circle. And then from A, once you get A, we're going to go to do the smaller circle that implies K, which implies G, which implies A. So in other words, if you wanted to get B implies K, you would have to do B implies A and then come to this circle to get K. Or D implies G, you would go D implies C implies B implies A, and then you'd be at this circle implies K implies G. Similarly, we have this other smaller circle. Once we're here at G, we can get to H and I. And then over here from D, we can get to E and F. And then from A, we're just going to get to L. So these are the different circles, 3 circles, and one straightforward proof. And to show where we are in the proof, when we're working on a particular proof, I'll outline it in yellow. So we're going to start with A implies J. So in other words, A is invertible, implies, I have to find J, there's a n by n matrix C such that CA equals I. So A is invertible, and I just wrote what it means to be invertible, that there's this A inverse times A equals A times A inverse equals I. Implies there exists C such that CA equals I. Well, since we have A inverse A equals I, let's let C equal A inverse, and then we've satisfied our condition. Next, we're going to look at J implies D, this part of the arrow here. So J is, there is an n by n matrix C such that CA is equal to I. It's sort of like the left-hand inverse. And that implies D. The equation AX equals 0 has only the trivial solution. So I rewrote that here. There exists C such that CA equals I, and AX equals 0 has only the trivial solution. So now we're going to consider AX equals 0. We can multiply both sides of this equation by C, so we get CAX on the left-hand side and C times 0 on the right-hand side. We know that CA is given to us, that that's going to equal to I. So we have IX on the left-hand side and c times 0 is just 0 on the right-hand side. Ix is equal to x, so what we get is x is necessarily equal to 0, and ax equals 0 has only the trivial solution. For our next proof, we're going to do D implies C. That is, the equation ax equals 0 has only the trivial solution, implies that A has n pivot positions. So I've rewritten it here. And in case you need a refresher on what pivot points are, is that first, we need to know a leading entry of a row. That's the first, counting from left to right, non-zero entry in a non-zero row. Then the pivot point in a matrix A is a location of A that corresponds to a leading 1 in a reduced echelon form of A. A pivot column is a column of A that contains it. So in this matrix, this isn't quite reduced echelon form because to be an echelon, oh, actually it is. Okay, so here, these are leading entries because they're the first non-zero entry, counting from left to right. And then there are also pivot points because they're leading 1s in a reduced echelon form. So here's our leading 1s. And it's reduced echelon form because we have the staircase and also the 1s have 0s in the rest of the column. So getting back to our proof, we're given that ax equals 0 has only the trivial solution, which means if it has only the trivial solution, that means it does not have infinite solutions. That's almost like, well, no solution is the opposite of infinite solutions, but it does not have infinite solutions, which means there are no free variables. Free variables correspond to infinite solutions. No free variables means that each row of A must have a pivot because it's square. And because it's square, then A has n pivot points. Next, we're going to prove that C implies B. That is, A has n pivot positions implies A is row equivalent to the n by n identity matrix. So given A is a square, n by n, and A has n pivot points, then A is square with n pivot points. That must mean the pivot points have to be on the diagonal. I've drawn this little 3 by 3 matrix here, and if there's 3 pivot points and the pivot point has to be a leading entry, that means that the first pivot point has to be in the top left. The next one has to be right on the diagonal, and the next one has to be the bottom corner. So anyway, so A has n pivot points and they are on the diagonal. So once you have your pivot points on the diagonal, by the time you get it in reduced echelon form, and remember in reduced echelon form, all your pivot points has 0s except where the pivot is. So that means you're going to have the identity matrix. And to complete this circle, we're going to show that B implies A, that A is row equivalent to the n by n identity matrix, implies that A is invertible. And what we're going to use is that theorem we had talked about in our earlier conversation, that to find the inverse, an n by n matrix is invertible if and only if it is row equivalent to I, and any sequence of elementary row operations that reduces A to In also transforms I to A inverse. And that was that example we had looked at when we were overviewing things. We said if we had a matrix A, we would row reduce A right next to I, and then we would keep row reducing until A became I, and using the same row operations on the identity matrix that we use on A, then what I becomes is A inverse. And that comes from this theorem here. Now we are on this next circle where A implies K. That is, A is an invertible matrix means there is an n by n matrix D such that AD equals I. So we have A is invertible, and that means we have A inverse times A equals A times A inverse, which is equal to I. Implies there exists D such that AD equals I. Well, this one's easy. It's kind of like that other one we said, well, let's let D equal A inverse. Then AD is equal to A inverse, which is equal to I. Next, we'll show K implies G. So there's an n by n matrix D such that AD equals I, and we're going to show it implies G. The equation AX equals B has at least one solution for every B and Rn. So we're given that there's this matrix D such that AD equals I. And now we want to show that AX equals B has at least one solution for every B and Rn. So we are going to consider B and Rn. Then somehow we have to introduce AX equals B. Well, I can't just throw in an A randomly. in front of an x and say it equals b, but what I can do is take b and I can multiply it by I, because I has this a in there, so somehow I'm going to get rid of the d later. So I'm going to multiply b by I, so I have ib equals I, and that works because, well, that's the identity matrix. Now, instead of I can introduce AD. So I have ADB is equal to B, and that's because AD is equal to I. That's given. Now I have three matrices, A, D, and the vector B. And remember, vectors are just one column matrices, so this is considered a matrix. And since matrix multiplication is associative, I can associate and do the multiplication of DB first before I do the matrix multiplication A. So now if you look, I almost have the form AX equals B, and I will have that form if I let X equals DB. That was my alarm. So I have X equals DB, and that's going to be my solution. And note that technically D is an inverse of A, so it's sort of like, this solution should look sort of like A equals A inverse D. D is, but just keep in mind that D in this case is the right-hand inverse, because matrix multiplication is not commutative. We have a left and a right-hand inverse. Next, we'll do G implies A, where G is the equation AX equals B, has at least one solution for B, implies A. A is an invertible matrix, so I have it written here. So given AX equals B has solution, and A is an n by n matrix, then A has a pivot in each row. We've already determined that, and that the pivots are on the diagonal. We've kind of seen this in a previous little proof. So that means A is row equivalent to the identity matrix, and from this theorem, which we've also seen in a previous proof, an n by n matrix is invertible if and only if it is row equivalent to the identity matrix. So we are done with this cycle. Next, we have G implies H, which is the equation AX equals B has at least one solution for each B in Rn, implies the columns of A span Rn. So we're given AX equals B has a solution for every B in Rn. And to show the columns of A span Rn, we need to show that every B in Rn is in the span of the column vectors of A. And that's just from the definition. So the span of the column vectors of A is equal to x1 times the column vector A1, x2 comes the column vector A2, all the way up to xn times the column vector an. So again, a1, a2, an, those are the column vectors, and x1, x2 up to xn, those are just real scalars. And remember, the span is a set of all linear combinations, so that's what I've written here. So we consider B in Rn, and we want to show that B is in the span of these column vectors, which means we need to show that B is a linear combination of the column vectors of A. So B equals x1 a1 plus x2 a2 up to xn an can be written in an equivalent matrix form. So we gather all the a's into a matrix times the real numbers, we gather it into a vector, and is equal to B. So, and we are given that AX equals B has a solution for all B in Rn. Therefore, B is in the span x a1, a2 up to an. In other words, the solution here, x, is exactly the coefficients in front of our vectors. Next, we have H implies I, so that H is the column of A's span Rn implies I. The linear transformation x to Ax maps Rn on to Rn. So given the columns of A span Rn, that means for every B in Rn, B is in the span of the column vectors, which means B is a linear combination of the column vectors of A. And we want to show that the linear transformation is onto Rn. In other words, we need to show that every B in Rn is mapped to, which is the same thing as saying there exists an X in Rn such that Ax equals that B. And I'm getting this simply from the definition of onto when we talked about that in the previous video that said for each B there exists at least one solution of Tx equals B. So we want to consider an arbitrary B in Rn, and we know since the column vectors of A span Rn, then B should be able to be written as a linear combination of the column vectors of A. And again, because the column vectors of A span Rn. Then rewriting this in matrix form, we have B equals AX. So that means there is the solution X that we get from here, from our linear combination, that will solve our equation B equals AX. And therefore, B and Rn, there exists an X such that AX equals B. Our next proof is I goes to G. So the linear transformation A to AX maps onto Rn implies G, which is the equation AX equals B has at least one solution for each B and Rn. So we're given that the X to AX maps onto Rn. That means for every B in Rn, there exists some X in Rn such that AX equals B. And we want to show, what do we want to show? G. That AX equals B has at least one solution. So we're going to consider B and Rn, and we need to show that AX equals B has a solution. So for every X, not for every, there exists an X in Rn such that AX equals B because we're given that the transformation AX maps onto Rn. And so that means we're done. There's an X that maps to B. I didn't do this last cycle and this last proof because, I left them for you, or you can look them up in your book. So the next two topics, first, if A and B are square matrices, then if AB equals I, then A and B are both invertible, with B being the inverse of A and A equals B inverse. And then also I just wanted to remind you these two definitions. Singular matrices are non-invertible. So if it's invertible, it's a non-singular matrix. That might be a good note. Whenever you put invertible, just put / non-singular. Whenever you say it's not invertible, then you should put / singular. Our first example is A invertible, where A has the column vectors 1, 3, -5, 0, 1, -1, -2, -2, 9. And the first thing I saw was B, I guess because, I don't know, it's right here under A is invertible. That's equivalent to saying A is row equivalent to the n by n identity matrix. So I did my row reductions, and eventually I could get to the identity matrix. That means that A is invertible. And actually, I could have stopped right here, because at this point, I have shown that A has n pivot positions. There's 1, 2, 3. I could divide, actually I should have stopped here, because there's this third pivot position. Because I just divide everything by 1/5. I kept my calculations when I was row reducing here, because I could also do E. The columns of A form a linearly independent set. So the columns of A are linearly independent means that the linear combination, all linear combinations of the columns of A equals 0 has only the trivial solution. So we can look at AX equals 0, so I row reduce everything, and I eventually get to this matrix, which tells me x3 is equal to 0, x2 is equal to 0, x1 is equal to 0. So AX equals 0 has only the trivial solutions, which by the way means the columns are linearly independent, which means that A is invertible. So actually, I had gone for this one, but I could have also stopped right here, saying that the columns are linearly independent. That would have given me that A was invertible, but I went ahead and said that AX equals 0 has only the trivial solution. That also would give me A is invertible. So there are a number of ways you could prove this. So the idea is you want to choose something easy for yourself if you want to prove A is invertible or any of these other things. So we're going to leave this theorem for now, and we'll look at invertible linear transforms. Remember, linear transforms can be represented by your matrix A. And now we can look for inverse transforms. I have this drawing we use to illustrate transformations. So if we have a vector x, the multiplication by A transforms it and puts it in another space. Here we're in square matrices, so we're just going from Rn over here, and the codomain is also Rn. But here we're mapping from Rn to Rn. Then the idea is we can have these inverses, which is also multiplication by A inverse. But these transforms will bring us back to x. So to get to the definition of inverse transforms, we want to recall that matrix multiplication corresponds to compositions of linear transformations. So in other words, when we multiply by A, and then we multiply by B, we do another mapping over to Rn. So that's like composition of linear transforms. And when a matrix A is invertible, then the equation A inverse A can be viewed as a statement about linear transformations. In other words, we can view this as this is A times X, which brings us here, and then we take AX, and then we apply this transform, A inverse, and that brings us back to X. So a linear transformation T from Rn to Rn is said to be invertible if there exists a function S from Rn to Rn such that S of T of X is equal to X and T of S of X is equal to X for all X in Rn. So this is like T would bring us over here, and then S would bring us right back to where we started. So sort of what you would think of as an inverse. Rather, exactly what you would think of it as an inverse. And we have this theorem of inverse transformations. If we let T go from Rn to Rn be a linear transformation and A is the standard matrix for T, then T is invertible if and only if A is invertible, is an invertible matrix. In that case, the linear transformation S given by S equals A inverse is the unique function satisfying S of T of X, and T of S of X is both equal to X for all X in Rn. So this right here is our definition for our inverse transformation. To prove this theorem here, there's an if and only if, right? T is invertible if and only if A is an invertible matrix. So here's the if and only if. So there's two things to prove. The forward direction, which is T is invertible, implies A is invertible, and the backwards direction, which is A is invertible, implies T is invertible. So we're given T is invertible. We want to show T is onto Rn, which will then imply that A is invertible. And here we're using the invertible matrix theorem. I said we were going to leave it aside, but I guess I lied. Anyway, so again, if we can show that the linear transformation is onto, then by the invertible matrix theorem, that means A is invertible. So we're going to start with B and Rn, and we want to show T is onto. Well, we do know that T is invertible, so there must be a function S by our definition over here of what it is to be invertible. That means there exists a function S, or transformation S, such that S of T of X is equal to X and T of S of X is equal to X. But then we can write that X is equal to S of B. Whatever B we're given, we just take the mapping S of B. Then T of S of B is equal to B, and therefore T is onto. And then by the invertible matrix theorem, that means A is invertible. Now we have the other direction to prove, that is A is invertible implies T is invertible. So we're given A is invertible, so we're going to let S be the inverse of A, so that S of X is equal to A inverse of X. Then S is a linear transformation, and then it satisfies this condition, these two conditions here to be an inverse. That is, S of T of X is equal to S of A of X, which is equal to, now S is A inverse A of X, which is equal to I times X, which is equal to X. And then similarly, T of S of X is equal to T of, and then S is, right, is our A inverse of X, which is equal to, T is represented by A, somewhere we said that, A of A inverse of X is A inverse, this is I of X, and therefore we have X. And by our definition then, what that means of invertible is that T is invertible. I have 3 more problems for you to try. Since we've covered everything in this video, after I give each problem, you should pause the video, give them a try before you look at the solutions. The first problem is to determine if A is invertible when A has the column vectors 2, 2, 2, 3, 3, 3, and 4, 4, 4. The first way I did this was using the invertible matrix theorem, saying A is invertible if the equation AX equals B has at least one solution for each B in Rn. So I chose a random B in Rn, and R3, because this is a 3 by 3. So that's B1, B2, B3, and that will be given. So these are not variables, but they are placeholders. And then my matrix A is 2, 2, 2, 3, 3, 3, 4, 4, 4. I row reduced, and I get 2, 0, 0, 3, 0, 0, 4, 0, 0, B1, B2 minus B1, B3 minus B1. So what I get here, this equation tells me B3 is equal to B1. This equation tells me B2 is equal to B1. And this top equation tells me 2 times x1 plus 2 times x2 plus 4 times x3 is equal to B1. But what I see here essentially is that B1 has to equal to B2, which has to equal to B3. So these conditions here tell me that not all B's have solution, right? If B1 is not equal to B2, then there's no solution. So this is false, which means that A is not an invertible matrix. An even easier way at deriving that this is not invertible is using E. The columns of A form a linearly independent set. So what I can see, though, is these aren't linearly independent because they're scalar multiples of each other, right? 4 is equal to 2 times 2, and it's equal to 4/3 times this 3 vector here. So they're linearly dependent because they're scalar multiples. That means they are not a linearly independent set, which means A is not invertible. That's the easier way to do it. The next question is, suppose that for a certain n by n matrix A, statement G, which is here, the equation AX equals B has at least one solution for every B in Rn of the invertible matrix theorem is not true. So this is not true. What can you say about the equations of the form AX equals B? And of course, there are lots of things you can say. You can say any of these statements are not true, but in particular, they want to know about this equation. What can you say about the number of solutions? So I said that G says that for all B and Rn, AX equals B has at least one solution. So we want to negate that. So we want the negation of this, which means we want a statement that makes this false, or just enough of a statement to make this false. So to negate, that's there exists a B and Rn such that AXB has no solution. So this is the negation. And I want to just, if you've taken a course in logic, this is, this is your quantifiers, and you negate, the negation of a for all is there exists, the negation of there exists is for all, and then you negate the rest of the statement. But just to appeal to your intuition then, if you have the statement everything is good, the negation of everything is good is not everything is bad. And by bad, I mean not good. The negation, or what makes this statement false, remember that's what we're saying is negation. The negation is that there is at least one thing that is not good. That will make this statement false. So again, to make this statement false, you only have to find one B such that AX equals B has no solution. So the important part is to make sure you include your quantifiers here, and you don't say that AXB has no solution. It's that at least one B has no solution. The last problem is suppose A and B are n by n matrices and the equation ABX equals 0 has a non-trivial solution. What can you say about the matrix AB? So what we have here is the equation AX equals B has a non-trivial solution. So if it has a non-trivial solution, that means the column vectors of AB are dependent, which here we have the column vectors of A form a linearly independent. So this matrix here does not meet this condition. Actually, even more to the point, there's this condition here. The equation AX equals 0 has only the trivial solution, so this does not meet this requirement. So what that means is the matrix A is not invertible. To review what we have covered in this video, we looked at characterizations of invertible matrices, and one of the main things we used to characterize invertible matrices was the invertible matrix theorem, which said if A is an n by n matrix, so again, one of the big caveats which you want to keep in mind is this is only for square matrices, and then 2, then the following statements are equivalent, meaning if any one of these statements is true, then all of the statements is true. Or if any one of these statements you find to be false, that means all the statements are false. And the invertible matrix theory is powerful because it connects so many important concepts. However, again, it should be noted that the theorem applies only to square matrices. We had this additional theorem: if A and B are square matrices and A times B equals I, then A and B are both invertible, and A is the inverse of B and B is the inverse of A. And we had this other definition I want to remind you about. Singular matrices are non-invertible, or another way of saying non-invertible is to say a matrix is singular. And then if a matrix is invertible, we say it's non-singular. Last, we looked at invertible linear transformations. Because linear transformations can be represented by matrix A, then it's natural then to ask about inverse transformations. And we define inverse transformations. So a linear transformation is said to be invertible if there exists a function also going from Rn to Rn, both of them are square matrices, such that S of T of x equals x and T of S of x is equal to x. So kind of what you would naturally think of as an inverse. And we have this theorem here. Let T go from Rn to Rn be a linear transformation, and let A be the standard matrix for T. Then T is invertible if and only if A is an invertible matrix. And in that case, the linear transformation S given by S of x is equal to A inverse of x is the unique function satisfying S of T of x equals x and T of S of x is equal to x for all x in Rn. And we call S the inverse of T, and we write S equals T inverse. So that's it for this video. Thank you for watching.